Hi everyone. Today we'll cover the system designed for search autocomplete. First, let's understand the use case, what we're planning to cover. First, we need to understand whether the autocomplete is for single words, as in mobiles, or is it for a complete sentence, like in a Google search. And should the search results be specific to a user, whether, uh, for example, in Amazon or Flipkart, e-commerce websites where the search results are specific to what the user has been searching and it is not in a generic way. And how frequently should the backend data be updated? So, for example, if it is Twitter or a newsfeed system, then the backend data needs to be updated very quickly so that if there's any breaking news uh, or something similar, it shows up in the search autocomplete results. And what languages should be covered, whether it's only English or any other languages. If it is any other language, then you can always use Unicode for the specific languages, but mostly the system design should remain the same. Okay. Now, let's go through the assumptions based on the use case. So for this video, we'll assume it is a Google autocomplete system where the string in English has to be auto-completed and there is no personal search ranking as required for Amazon or Flipkart. And the backend data will not be updated often. A weekly update should be sufficient for a Google search. And only English language is supported. The daily active users will be around 10 million. And each search will have on an average of 20 characters. Each user will make around 10 searches in a day. And you can assume that 20% of the searches are new searches. And we need to return only the top five searches, top five frequent searches. Now, estimations based on these assumptions, 20% of the 20 bytes into 10 searches into 10 million users is 0.4 GB for new search data every day. So that is minimal compared to the amount of data that is stored in for a Google search system. And ops per user will be 200 by 24 by 3600 seconds. And ops for 10 million users will come around 24,000. So 24,000 ops per second. Now, on a high level design, we can divide the system into two services. One is for a data gathering service, and the other is a query service. The data gathering service basically collects the input queries, aggregates them, counts the frequencies, and keeps the data updated for the query service to search the data for the top five results. So that's basically the idea about data gathering service. Query service is, of course, to go over this data and mm, get the top five queries as fast as possible. Now let's consider a small data set with 4 to 5 words and their respective frequencies mentioned here. So for this use case, we'll be using a trie data structure, which is basically a character wise or an alphabet wise data structure with each node having, say, if it is English, 26 characters per node, 26 children per node, and we'll form the tree as shown in the diagram. So the T will have, say, TR and TO, and TR will extend to TRE and then tree. And the tree node will indicate basically a word, and it will also, we can store the uh, entire data set in this way. Now, in this trie data structure, we can also update it with the frequency for each of the words that are searched. This way we can identify which are the top, say, five searches by uh, parsing the tree. Now, parsing the tree might be a log n operation, because at a parent, say if the user types tr, then the query has to search through all the child nodes of tr parent and get the top five results and send it back. But this can be optimized by storing the top five results at each of the nodes. Of course, this will consume more storage, but it's a trade-off for lower latency. Now, if we store the results at each node on what are the top five search results for each of the nodes, then the results can be retrieved in O of 1 complexity. And this data can be stored in a hash map where each node maps to a specific key. So, uh, getting the data is also quick, where the key of the hash map will be the node value, and the value will be node name, as in t or tr or tre, and the no hash map value will be the top five or top k results, top k search results for that time complexity will be O of 1. Now, going through the data gathering service, from the search logs will be a O of 1 operation, where the logs are only appended and there is no updation or removal of the logs. From these logs will be sent to aggregators, and the aggregators will retrieve the aggregated data. The workers will get the work parse the aggregated data and will update the try-db accordingly on a weekly basis for this use case. And the try-db snapshot will be updated to the try cache on a weekly basis, which will be used for the query service. Now, the query service will get the data from try cache. And of course, if it is not there in the try cache, it can check on the try-db. Now, coming to the query service, the query can come either from a web browser or a mobile. The API will be sent to a load balancer. From the load balancer, it goes to the API servers, and the API servers will talk to the try cache to get the data and try DB if it is not there in the try cache. Now we can use Ajax for the UI, because by using Ajax, we need not load the entire UI for every query. Only the portion of the UI which needs to be updated can be loaded. And we can also use the browser cache to store the query results with a specific time to live value mentioned, so that if the frequently searched queries can be quickly retrieved from the browser cache instead of sending the query to the uh, servers for faster retrieval. And we can also use filters to remove hateful, violent, or dangerous data from the results. This can be done either at the parsing end, where we are updating the try-db, which ensures that um, we get the top five or top k results, or it can also be done before sending the response to the user. Now, scaling uh, the DB can be scaled based on the amount of data that needs to be stored per prefix string. For some prefix strings, the data will be high. So some prefix strings, the data will be less. So it can be combined and stored in different nodes. Say, for example, all the if there are many words starting with S, then all the words starting with S can be stored in a specific node. But if there are very few words starting with X, Y, and Z, then all the words starting with X, Y, and Z can be stored in a single node. And that way we can distribute the data storing based on the prefix string. And if the word starting with S increases, or the search string starting with S increases, then it can be divided into multiple other nodes like SA, SB. Mhm. Uh, I'd like to credit the system design interview book by Alex here for diving deep into these concepts. Uh, and the writes can be made asynchronous by sending it to a Kafka queue and then ensuring that the service is not impacted, the search service is not uh, impacted because of the latency of the write operations. So the data can be retrieved from the Kafka queue and then sent to the data gathering service to update the try DB so that the querying API servers are free to address the um, GET requests. Right. So moving on now, if we want to modify this slightly for a Flipkart or an Amazon e-commerce service, we can have independent try data structures maintained for each of the users to have their specific user level search autocomplete data. However, this might not be ideal as well if the try data structure is very small. So what we could do is probably merge some of the user results, similar user uh, try structures into a single try data structure. That way, the relevant data can be retrieved from a single try data structure. Say, for example, all the users in say Bangalore or Mumbai can be mapped to a single try data structure with the assumption that their search queries are similar. Now, if the search autocomplete is for a Twitter or a newsfeed system, which needs to be updated frequently, we can update the try cache based on the frequency of change in the nodes in TryDB, in the sense that if a particular search query is queried very frequently, say it increases from 0 to 1,000 within a minute, then we can trigger a updation to the try cache so that it is always up to date in terms of uh, the relevance of the search results. So this way, the updation of try cache need not be on a frequency basis like a weekly or a monthly basis, but it can rely on the frequency of change in the search strings. And the time window between two back-to-back updations can be configured as in order to ensure that there is no frequent update of the try cache. We can maybe space it out by adding a 5 minute or a 10-minute window between two updations to ensure that the try DB is not overloaded. Um, I think we have covered most of the use cases with respect to autocomplete. The only aspect maybe I didn't mention at the end is that if we have to cover multiple languages, then uh, we can use Unicode strings. Okay, thank you everyone. Please do let me know if there are any questions.